Hello, everyone. Today we're going to go over, finish up your notes on your impulse and momentum notes, going over the law of conservation of momentum. Pull up your slides. These here happen to be posted. They have the same information. But before going through and defining the law of conservation of momentum, we have to define what a closed or isolated system is. A closed or isolated system is one where there is no energy lost. There are no outside forces that will affect the system. So that means that there is no friction. So out of the Newton's Cradle lab that we did before this lesson, there's no air that would come down and slow the ball down as it's before it's crashing. There's no sound being emitted or energy lost that way. Everything gets transferred, that there is no outside forces that affect what's going on in that particular simulator. Because even if we would have let the Newton's Cradle swing back and forth for as long as we could, it's eventually going to end up coming to rest. Whereas on an actual simulator, if I do that, where there are no outside forces, that would end up going on forever as long as the computer has power. It's going to keep swinging back and forth. So, with a closed or isolated system, the law of conservation of momentum states that the total momentum in a closed or isolated system does not change. Simply put, the momentum before a collision equaled the momentum after a collision. And this was something that I was hoping that you would have noticed yesterday as you were doing your lab. And that was right here. So in the lab, if I had two balls being released from the one side and one being released from the other, I have two swinging down before the collision to the right. I have one swinging down from the left. And after the collision, one continued going to the left and two shot out to the right. So I'll do this again. Play. Two went right, one went left. Momentum was conserved. Whatever momentum I had before the balls hit, that was going to be the momentum I had afterwards. Okay, back over to our notes. View, slideshow. Okay. Now there's three different types of interactions that we'll look at. So this is where two objects are either crashing into one another or something happens and bam, they go off their opposite directions. The first one is an elastic collision. This is where objects collide and they bounce off of each other. So an example, if you ever shot billiards, or it's often called pool, where the balls hit, they bounce and they roll opposite directions. Maybe bowling balls hitting a pin, Newton's Cradle, that would fall under the elastic where they hit and they bounce. In any elastic collision, the objects collide and they stick together. That's the key word with any elastic, is the fact that they stick. Examples include, we have train cars collide and stick together, cars that stick together after a crash, maybe someone jumps onto something, but basically they move off and they go together with the same final speed. The third one is what's called a recoil interaction. So with a recoil interaction, there's nothing happening at the start. So both objects are at rest. And if both objects are at rest, the total momentum before is zero. But then something happens. You pull the trigger. You jump forward from an object that's on wheels. One object goes forward, the other one goes backwards. That's why if you're ever shooting a rifle, they always say to put the butt of your rifle in your shoulder. Because when you press the trigger, all that momentum from the bullet that's going forward has to be canceled by the momentum going backwards. And that's why the gun comes back. So an example, shooting a gun, throwing something on skates, jumping off of a boat, those would all be examples of a recoil. So now what exactly will that look like? Well, maybe for an elastic collision, here's a couple different examples. Elastic collision, they hit, they bounce. even though this has a plus dot dot dot, the dot 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 means that you can have more than two. You just end up with an extra momentum term. Now, you don't have to memorize this equation. This is provided on your equation sheet. This is the elastic collision. All this is m times v. We're finding the momentum of the red object before the collision. Then we're going to add it to the momentum of the white ball before the collision. Then the equal sign, that's the collision part, happens. Then this over here, this is our after side. We have the m times v, so I find the momentum of the red ball. And then there's the m times v, I'm finding the momentum of the white ball. And what the law of conservation of momentum says, that the total momentum before has to equal the total momentum after. So if I add up the momentum of both balls before, that has to equal the momentum of both balls after. Maybe I have this type of interaction. The red ball's moving to the right, the white ball's moving to the left. Both objects have momentum. Again, I would take the object's mass, multiply by its initial velocity, then add it to the white ball's mass times the velocity. I'm finding the momentum of each object. The momentum of both of the initials has to equal the momentum of both finals. Or maybe you have this type of interaction. The red ball's moving a little faster, comes over, taps the white ball. The white ball's moving slower since it has a smaller arrow. The white ball gets momentum transferred to it. It's going to start increasing its speed. But where did that come from? That had to come from the red, so this one decreases its speed. The total amount of momentum has to still be equal. That's elastic collisions. For an inelastic collision, the equation changes slightly because we have like term over here. This is the same final velocity. That's why I add the masses together. That'd be like m1 times x plus m2 times x. If it's both x, the same variable, I can combine like terms. So if you're ever unsure which one to go with, always start with elastic collisions first. Always start with this equation because all the other versions come from this one right here. For this one, so we get momentum of the blue car plus the momentum of the red car. If I add them together, the collision happens. Since these have the same final velocity, I end up with m1 plus m2. They will have the same speed. Now, this one here has to lose momentum because this one gains momentum. The last type that we'll talk about is what's called a recoil problem. So recoil, the left side becomes 0 because m times 0 is 0. Anything times 0 is itself, or is 0. So that's why the m1 v1i plus the m2 v1i ends up being 0, and that's where this equation comes from. Before, there's no total momentum, so afterwards there cannot be any momentum either. So the momentum m times v has to equal the m times v of the gun going back the opposite way. Okay, so when we're doing problems, very important, please make a sketch. All you have to do is draw it out, like what's happening before, one object's moving, which way, another object, what is it doing, then the after sketch. Make a data table for each object. Object 1, object 2. What's the mass and what are the two velocities? Make sure you watch your signs because velocities can be positive or negative depending upon which way it goes, because velocity is a vector quantity, meaning it has magnitude and direction. Make sure you pick the right equation. Again, you will not go wrong if you start with the equation for elastic if you fill out your data table correctly. The elastic equation is the first one that is listed on your equation sheet. For an inelastic collision, they have the same VF, or both VS will be missing from your data table. So here's an example of me going through and making my sketch. I have a 1875 kilogram car going 23 meters per second. That's traveling to the right. Rear ends a 1025 kilogram car going 17 meters per second on ice in the same direction. The only reason why we mention on ice is because with ice, there is no friction. So that means that momentum is conserved. The two cars stick together. If they stick together, they move off with the same final speed. That also gives me a hint about what type of interaction I have, whether it is an elastic, inelastic, or recoil. It wants to know how fast do the two attached cars move immediately after the collision. So I made my sketch. One's moving 23, another one's moving 2017. Afterwards, they're both moving together. So if I fill in my data table, that gives me 1,875 kilograms is the mass of cart 1. It's going 23 meters per second. The way I drew this was to the right, so that ends up being positive. The 1,025 kilogram car is going 17 meters per second. How fast do the two cars move off immediately after the collision? Now here, I don't know either final velocity, but it also gives me a big hint. I highlighted it right there. The fact is that they stick together. Another hint that I have a certain type of interaction is the fact that I don't know either final velocity. Since they stick, this means that this is an inelastic collision. So that means for my equation, this is M1 VI plus M2 VI equals, inside of parentheses, M1 plus M2 times VF. I do suggest writing down your equation. It's easy to plug in the wrong things. When you're going through and doing this, when you have the ones, make sure you're reading from table 1. When you're doing the 2s, read from table 2. So M1, 1,875, that's my mass, times the initial velocity, 23. M times V. All I'm doing is finding out how much momentum does each object have. I'm going to add this to the momentum of object 2. 1,025 times 17. Again, momentum of cart 1 plus momentum of cart 2. This is all the initial side on the left. On the right, it has to equal the total momentum of the remaining car. So M1 is 1875 plus 1,025 times VF. Now it's time for simplifying some terms. 1875 times 23. This gives me 43,125 plus 10,000 or 1,025 times 17. That's going to give me 17,425. That's going to equal 1875 plus 1,025, 2900 VF. I want to simplify the left-hand side, 43,125 plus 17,425. 44,870 is equal to 2,900 VF. And the last thing to do is divide both sides by 2,900. 2900. And VF is 15.5 meters per second. All right, and that should conclude the rest of our notes. Please be mindful, again, what this happens to show is our different types of interactions. The elastic, they hit and they bounce. So I'll show you guys here. So an elastic, if they're coming together, I hit start. So this object has momentum, this doesn't. This momentum decreases because this one gains. But if I look at the total momentum before, that's going to equal the total momentum after. If it's an inelastic collision, they're coming together, they hit, they both move off with the same final speed. But the key thing with an inelastic collision, they hit and they stick. For a recoil, or as this simulator likes to call it, an explosion, nothing is happening at the start. Bam, there's an explosion. One object goes one way, another object goes another. And that concludes our notes.